Hi, and welcome to an introduction on operational amplifiers. So far in this class, you've learned about passive circuits. Passive circuits are only capable of filtering because they do not supply power. We will now discuss active circuits, which are powered and can supply amplification or gain. Both of these circuits can utilize resistors, inductors, and capacitors. This video will focus on operational amplifiers, or op-amps. Represented as triangles, these are differential amplifiers, meaning they have an inverting and non-inverting voltage input. The non-inverting is indicated by a positive sign, while the inverting is indicated by a negative sign. Op-amps are powered by a negative and positive voltage source. The voltage supplies act as limits for the voltage output. The output is saturated when the inputs are different. We can compare the output voltage on the y-axis against the differential input on the x-axis to better see this relationship. The output is capped or saturated at the positive voltage supply value when the non-inverting input is greater than the inverting. It is saturated at the negative voltage output when the inverting input is greater than the non-inverting. Op-amps operate in the linear region, meaning they function in between these values. The slope of the line between them represents the voltage gain or the amount of amplification occurring in the circuit. When the inputs are about the same, this relationship is steep and there is high amplification or gain. The basic schematic shown here shows the linear circuit of an op-amp. The voltage difference between the two inputs is equivalent to the current multiplied by the input impedance. The voltage difference multiplied by the internal gain results in a voltage source that runs across an output impedance. The result is a voltage or current output. The voltage output is the gain multiplied by the voltage input difference minus the output impedance times the current output. These can be determined using basic nodal analysis. Note that A is the voltage gain and Rn and Rout are the corresponding impedances. Ideal op-amps have infinite gain, infinite input impedance, and zero output impedance. Ideal op-amps also assume that no current goes into the op-amp at either input, as depicted, and that the input voltages are equal. Note that for this class, all op-amps are considered ideal. Note also that an ideal op-amp may still saturate. While its gain is infinite, as soon as the output reaches either the positive or negative rail, it will be limited and can't go outside of that range, so that for any differential input voltage that is different from zero, the output will be either the positive or the negative rail depending on the sign of the input. In this regime, the ideal op-amp is actually a comparator, which we'll discuss later. In contrast, the active or linear mode of operation of the op-amp is where the differential input is zero and the output is strictly between the rails. In practice, the op-amp reaches that linear range of operation only by providing negative feedback. In the case of zero feedback or positive feedback, the op-amp turns into a comparator or a hysteretic comparator. To analyze these circuits, first label any unknown node voltages, then apply KCL on all nodes except the op-amp outputs. Add the equation that Vn plus and Vn minus, the input voltages for each op-amp, are equal, then solve. You should have equal equations to unknowns. Thanks so much for tuning in. I hope this video has helped.